Hi everyone, well done. You found the link to the Composites Cluster presentation of the Bernal Research Day at the Bernal Institute here. So I wish you a warm welcome from wherever you are. It's afternoon here in Ireland, and I hope you're sitting comfortably. It gives me great pleasure to introduce Professor Brian Falzon from Queens University Belfast to you this afternoon. I've known Brian for many years. I think it's 21 years since we were relatively junior academics back in the UK, Bristol and Imperial College. And we both had a journey since then. Brian has a sort of longer journey. I'm going to read Brian's bio in a minute, but from my perspective, I've always, first of all, admired Brian's rigor in his science, particularly in structural mechanics, which relates directly to my own specific area of interest and expertise. I think he's always cut to the quick and shows problems very clearly and describes them very well. And beyond that, I've really enjoyed his company at conferences and our meetings since. So without further ado, I'll give you a little bit of his bio. So Brian joined Queens University Belfast School of Mechanical and Aerospace Engineering as the Royal Academy of Engineering Bombardier Chair in Aerospace Composites. This is a very prestigious and sought after position, so congratulations on that, Brian. And then he's shone since then, where he subsequently established the Advanced Composites Research Group. In 2015, he took up the role as head of school, and prior to Queens, and after leaving Imperial College, Brian held the Foundation Chair in Aerospace Engineering at Monash University, Melbourne, Australia. And between 1996 and 2006, he was at Imperial College, as I mentioned, in Department of Aeronautics, and he's a graduate of University of Sydney, where I note he has not only a PhD, but BEng honours in aeronautical engineering and BSc in physics and maths. So a bit of a polymath there, Brian. Without further ado, I let you continue with your talk on the use of highly aligned carbon nanotube webs in multifunctional composite structures, which I wanted you to deliver because I think it is of specific interest to people at Bernal and elsewhere, but is also of appeal to a general audience. Thank you, Brian.
Thank you, Paul. Paul, can you confirm that you can see my screen?
Yes, I can see your screen.
So you can see the Queen's University Belfast logo?
Yes, the IT seems working.
Okay. Right, so thank you everyone for joining me this afternoon. As Paul said, I'm going to be talking about specifically the use of highly aligned carbon nanotube web in multifunctional composite structures. And the way I've structured this talk is I'm going to first of all describe what a CNT web is and how we make it, very briefly, of course. And then I'm going to focus on three functional aspects or three uses that we have found for this web. One of them has to do as a heating element in an anti-icing, de-icing device. The other one as a strain and damage sensor, and also for thermoplastic welding. Now, I should also mention that this project formed part of a larger project which was sponsored by the Engineering and Physical Sciences Research Council here in the UK, where we were actually looking at multifunctional hierarchical composite structures using different carbon nanotube architectures or assembly. But I'm going to focus this talk on the use of one particular type of assembly, which is a carbon nanotube web. Now, what I will say, though, is that we have looked at using carbon nanotube forests as interfaces. You can also spin these webs into yarns and use them in that capacity. And you can see some of the multifunctional aspects that we looked at. I'm not going to talk about fracture toughness enhancement, primarily because I feel also that it's been covered by so many others using different types of architectures. But as I said, I'll focus on the other. And lightning strike protection is also something I will not be talking about today. It is stuff that we are working on right now, and I will say from the onset, it is probably the most challenging, and that's why probably I'm not talking about it today, because I want to move the science a bit further along before we can report on it, and also there are some sensitivities there with the company that we're working with. Now, let's just look at carbon nanotubes. You know, for some of you, I'm sure would know what these are and what's claimed of them. And the challenge for us, if you look at some of the outstanding singular properties, they've got, you know, very low density, extremely high stiffness, strength. Your thermal conductivity is actually higher than, say, diamond. Diamond's about 2,000 watts per meter Kelvin. Silver's only about 400. And electrical conductivity is also very good. Not as high as copper, but very close. The challenge for us has always been, how do we translate those properties at the nanoscale to the macro scale? And this is what we have tried to do, at least with some functionality, when it comes to a carbon nanotube web. So what is a carbon nanotube web? So the way we make it is that we have a quartz tube here. We have a silicon wafer with a catalyst, which is usually iron, and that's a very, very fine catalyst layer that we put on that silicon wafer, usually with an electron beam, but you can use lower types of technologies like a sputter coater. And then when you heat this up, you get a fragmentation of that catalyst, and they serve as initiation sites for growing your carbon nanotube vertically. And let me just bring my pointer up. As in, you grow them vertically, and we call that sort of a carbon nanotube forest. And the way we do that is that we have acetylene as the gas through which we extract the carbon, and we've got helium. There's a whole protocol on how you do this, and there has been a paper published if anyone's interested, and you can see the reference at the bottom of that of this slide. And what's interesting is that the carbon nanotubes actually grow from below. The carbon is drawn in onto the catalyst, and then the carbon nanotube extends upwards. Now, what's nice about this is that the carbon nanotubes are very clean. There's no catalyst. There are other methods of producing these. You can do this with what's known as a catalyst co-injection method, where what you end up with is a randomly highly entangled mix of carbon nanotubes and catalyst. But of course, our catalyst remains on the silicon, and what you've got is this nice forest. Now, what's interesting about this, that if I get that silicon wafer, and then and you can see it at the bottom of this image here, what you will see is that wafer, we've got all those carbon nanotubes sitting upright as in a forest, and then we can just get one edge and draw those carbon nanotubes out. And the way and you can think of these, they're vertically, but then when we draw them, they sort of fall onto their side and are held together by van der Waals forces. And that's all that's keeping that web together. So if I can show that again, I'm not sure how well you can see the video, but that is a very, very thin web of carbon nanotubes. All the carbon nanotubes are highly aligned, and as I said, just being held by van der Waals forces. Now, what's nice about this is that because they're so highly aligned, then we can make use of their directional properties. If you look at the the X winder here, if I can get the video going, hopefully. For some reason that's not going, but we've got this silicon web, the silicon wafer here again, and we are drawing the carbon nanotubes on this winder, and as it rotates, it draws the carbon nanotubes out. And we can, with the reason why we've done this is that because with the winding mechanism, we can alter the direction at which we wind those carbon nanotubes onto that surface. So that gives you something of the background. Oh, there we go, it's going now. So you can see how those carbon nanotubes are drawn very smoothly. The web is very regular. Right, so let's talk now about using them for anti-icing and de-icing applications. Now, when we talk about anti-icing, what we usually mean there is the prevention of ice buildup, and de-icing is when you remove ice which may have formed on a lifting surface. So de-icing, you'll see that happening if you're sitting out on the tarmac on a cold day in an aircraft, and you get these you get the facilities coming out to spray a glycol-based solution on your wing, for example. There's infrared heating. I know in the US there are these sort of large sheds, hangars, where you can bring your aircraft in, and you've got all this infrared heating to melt any ice that's being built up over your aircraft. And there are some other newer methods like electro-impulsive methods. The pneumatic bladder has been around for some time. You find that quite often on smaller aircraft, where you've got a bladder around the leading edge, and then you just basically expand that bladder and break the ice that may have formed on it. And the method that the newer methods now are electrified, they're electrothermal, and with anti-icing, the most common method of anti-icing is through hot air bleeding from the compressor stage of your power plant. And you've got, so if we look at a leading edge here, you've got piping with holes in it, in that piping, which allows that hot air to come through, heats the inner section of, say, the leading edge, and then increases the temperature enough to dislodge the ice. And with anti-icing, you can also have an electrothermal approach. Now, the Boeing 787 has such a system on board. It developed by GKN, where there's a metal spray which is encapsulated between glass fiber laminates. Now, what's nice with the carbon nanotube web is that we can use that as the heating element, but it's tunable, and I'll explain what I mean by that. Before I do, I want to also mention that there are other potential uses in terms of anti-icing and de-icing. We are working with what were Bombardier up until a month ago. Now they are now Spirit Aerosystems, just down the road from us here, looking at heating the nacelle intake. Currently, the approach is very similar to what I mentioned earlier, where you bleed hot air from the power plant, and then you distribute it around the surfaces that you want to heat up. Now, of course, with all this pipe work, you've got extra maintenance, additional weight, etc. Electrification. The onboard electrification of systems is something that the aircraft industry is moving towards, and that's why electrothermal systems do make a lot of sense. Wind turbines are also another area where this type of technology would be quite useful. The one reference did claim that up to 20% production losses is due to cold climates. And the thing here also is that quite often these are massive structures. They can get into, these blades can be quite large, and getting any appreciable large ice shedding off these blades can actually cause quite a bit of damage to not just the blades themselves, but also to any surrounding infrastructure. So if I now look at the web itself, we started looking at the initial investigation was to compare a CNT web with the direct heating of carbon fiber UD plies. And if you look at resistance versus the thickness of either the carbon nanotube layer, because obviously I mentioned what you saw was a single layer being drawn out, but of course you can stack these up. And if we all stack them up at say 10, 20, 30 layers, then you can look at how your resistance changes. And as you would expect, we're not talking about resistivity here, we're talking about resistance, right? So as you would expect, your resistance drops as you increase your thickness. Now, if I take one particular set of data points, which we've got 8 plies of carbon fiber, the weight there is, as you can see there, 3,634 grams per meter squared, right? So comparatively heavy when you compare this to 20 CNTs, where you've only got 0.38 grams per meter squared, right? So you're going from kilograms to a fraction of a gram. So from a weight perspective, these things weigh next to nothing. And the way that we tested these carbon nanotubes, and indeed even with the carbon fiber as heating elements, is to put them between 2 glass fiber plies. And what I will also say is that because they are so light, they don't have much thermal mass. So the heat up rate for the carbon nanotube as a web, as a heating element, is much steeper compared to, say, the carbon fibers. As a comparison here, there was some recent work looking at Constantan wires, which is a copper and nickel alloy in a leading edge. And you can see there how the surface temperature is actually quite non-uniform because you've got these discrete elements. What you see here also is how uniform the heating distribution is with your carbon nanotubes as the heating element, even compared to the carbon fibers. So we wanted to look at how we might use these as both anti-icing and de-icing. So for the anti-icing experiment, what we did is we actually performed, we put a barrier right over the sample like a bund, and then this is the carbon fiber structure that we then had our heating element on, and we placed 3 millimeters of water and applied a constant voltage of 10 volts for this particular system. And we wanted to see whether whether ice would form or whether we would prevent ice from forming using different carbon nanotube, different numbers of carbon nanotube layers, and as a comparison using different carbon fiber plies or layers. And what you will note is that if we do have only a few carbon fiber plies or 10 carbon nanotube webs, then we really don't get much. We don't prevent the buildup of ice. If we then increase the thickness, we increase the heat going into the system, we get some partial melting. And then you can see how we can get complete melting once your carbon nanotubes your number of carbon nanotube web layers is about 30. In fact, it's more than you need. You get complete evaporation of the water. That's why you get that jump in temperature. So we've also done an analysis on the power requirements, which also shows that the system is also very efficient. We've also then looked at de-icing, where we basically froze the water over the sample, and then we mounted the sample vertically so that we can have gravity helping to remove the ice once we started heating the element. Now, what you will note again is that you get a different response in terms of the time taken to remove the ice, depending on the number of CNT webs that you use in your assembly. Now, with 40 layers of CNT web, the accreted ice was removed in about 15 seconds, so it was pretty quick. Now, I mentioned earlier that these webs are tunable. And what I mean by that is, well, for starters, you remember how I talked about you can grow your carbon nanotube webs initially vertically as a forest? Well, you've already got two parameters that you can play with there to tune your conductivity. You've got the height of that web, the height of that forest rather, or the length of the CNTs, the aspect ratio of the CNTs. You can also control the density of that forest. And I should mention that the way we grow them, as as you saw from that video, they're pretty transparent. You've got about 80, I think there's an 80% optical transmissibility. And so you've got those two parameters, but then because these are so highly directional, they have orthotropic behavior, so that their conductivity along the carbon nanotube draw direction is very different to the conductivity orthogonal to that, just like the stiffness and strength characteristics of a carbon fiber ply. And what we have done is then to look at laying up. We made a number of samples, so we made two types of samples. One with a low aspect ratio, as you can see here, and so the reason why I've drawn it this way is that if I wanted, say, my nanotubes to be at 45 degrees, well, I've cut at 45 degrees, and then I've got my electrodes on either side, and you can see that the aspect ratio there is pretty low. But I can also make much longer specimens so that I can look at the influence of the aspect ratio of conductivity, because it does make a difference. And if I look at so this is now we are trying to predict the conductivity as a function of orientation of that web. So I've got here, this is because the web is so thin, by the way, we consider it as a two-dimensional material, and we've got our current density here. This is our conductivity tensor, conductivity matrix, and this is our electric field. And what you will note is that if I look at a sample here, if my what I've called my length here is very small, as opposed to that length being very large, or the system, the aspect ratio approaching infinity, the conductivity as a function of angle is different. Now, you will note here that for the case where this is very long and thin, the conductivity is lower than when you've got what might be termed as an infinite web. And that kind of makes sense because let's assume that this is actually very long and thin, and you've got your fibers, your CNT webs at 45 degrees, then there is no direct carbon nanotube path connecting the two electrodes, right? So what we did then was, these are the theoretical curves. Of course, when I say theoretical, we do have to actually base those theoretical curves on two measurements, the one at 0 degrees and the one orthogonal to get our extremum points. But then if I start looking at the different samples I mentioned earlier, you can see that, as you would expect, with an aspect ratio of 1, 4, 9, etc., you fall between those two curves as expected. So in other words, we can predict the sort of conductivity you are likely to get from an orientation of that web. Now, of course, we can lay them in different directions, and then again, by analogy with what you would do with a structural directional orthotropic material, you can add these up. You can add the contribution of each orientation, and then you can measure or predict the conductivity of that stack. Now, this is a busy slide, so I won't spend too much time on it, but I will just explain what I've got here. So I've got a lot of carbon nanotube layups here, as you can see, and then I've got the calculated conductivity for a very low aspect ratio and the conductivity for a very high aspect ratio. Now where one approach is 0, the one approach is infinity. Of course, experimentally we can't do that, so I've got for comparison an aspect ratio of 1 and an aspect ratio of 4. And what you will see is that when your sample has a significantly biased directional layup, like 1 to 5, then the aspect ratio has a noticeable effect on conductivity. But where you've got isotropic conductivity, which may be the result of, say, having orthogonal layups, then what you find is that you don't have that level of sensitivity. Okay, so and you can see here some of the images, some of the thermal images that we get from those different types of CNT layups. Now, we've done a lot more work here also looking at the repair of these structures, and we can repair them, and we have shown we've got a protocol of how to repair these webs. You don't repair them, just say we looked at impact damage. You don't try and repair that impact damage with a web. You can just use a mixture of carbon nanotubes and a resin. Just all you need to do is to recover some sort of conductivity. Okay, so that's all I'm going to say about anti-icing, de-icing, or indeed any other use that will require some sort of heating. I want to now move on to some of the work that we've been doing in using the same web for structural health monitoring and even a strain measurement. Now, I'm sure most of you would be familiar with structural health monitoring. The attraction here is that it affords the possibility of condition-based maintenance, condition-based monitoring. And there's also the added incentive here that as we move away from mechanical fasteners and replace with bonding, perhaps there is an opportunity to somehow monitor that bond using structural health monitoring. Now, this has been looked at by a number of researchers. For the most part, what researchers have tended to do was to disperse disperse carbon nanotubes into an adhesive, and then look at some percolation threshold where you've got enough carbon nanotubes there to give you some sort of a conductive resin or a conductive adhesive, and then you can look at the changes in resistance, say if you put this adhesive between in a joint. Now, when you do that, you can see that you do get a change in resistance with the accumulation of damage, as you would expect. Now, what are the challenges with this type of approach? Well, consistency is one of them. Dispersion is also not an easy thing to achieve with carbon nanotubes. And even in terms of preparing these, the use of solvents and other chemicals which are not so environmentally friendly. Now, what's nice about using a carbon nanotube web, and what's remarkable here, is that we can use very few webs. This is some information on the carbon nanotube web, which I mentioned earlier. Probably what I didn't mention was the web is made out of multi-walled carbon nanotubes, and they're about 300 microns long and about 7 walls in terms of the number of walls, with a mean diameter of about 10 nanometers. So if we put so what we did here was to put a web, and a single web at that, just a single web at a joint, and then wanted to find out how we can measure or see how well they can behave as a strain and damage sensor. So there's our setup. They've got some, I'm not sure whether there's no sound there. If you can hear sound there, ignore it. What you will note is the following. First of all, I want to state that we actually looked at mounting these webs in the direction of the loading and orthogonal to the loading, and I will explain how the behaviors were different. But as you can see, I'm not so sure how well you can see the bottom left-hand graph. What you will note is you've got the load versus, well, this is our load. Well, let's move one above. You've got your load versus displacement curve here, and we've repeated it down here. The first question you might ask is, well, if I put this carbon nanotube web, will it compromise the structural integrity of that joint? It doesn't. In fact, for some reason, we get a slight increase. I'm not sure why. I don't believe that a single web can influence to that extent, but at least we know that there is no degradation in structural integrity. And what we know then is if I draw your attention to the red curve, we can measure the change in resistance, and before any visible damage at the joint, we start measuring a change in resistance, and that accumulates as the damage accumulates. Now, I mentioned that we've got carbon nanotube, the web also aligned orthogonal to the loading direction, and it's not very sensitive. And the reason why it's not very sensitive is because nothing that we are doing to that web when those nanotubes are orthogonal to the loading direction is affecting the resistance. Now, the resistance, that the change in resistance that we can measure when we load in the direction of the carbon nanotubes is a combination of the intrinsic resistance of the carbon nanotubes themselves. You've got the overlap of the carbon nanotubes, and indeed that resistance also includes tunneling, right? So we know that carbon nanotubes within a very, very short distance of each other can transmit electrons. Now, when we look at the response of the joint to loading, I know that I'm probably going a bit over time, so I'll hurry up a bit. What you will note is that the if I look at my displacement, this is given by the grey line, and under cyclic loading, you can see that my change in resistance follows quite closely. Now, for this particular specimen, the end displacement at failure was about 2 millimeters, so I'm loading at about 4.5 millimeters. Now, you can see that if I then start loading at a much higher displacement, I'm starting to induce damage, and that damage or the inducement of damage, permanent damage, is manifested by an increase in resistance that I'm measuring through that carbon nanotube web. And you can even, if you look closely at the features of the response, you can actually look at such things as whether the damage is the result of crack reopening or elastic deformation or the creation of new damage. So again, quite a sensitive damage sensor. And of course, we've done other. We've looked at different cycling rates. I won't go into any details here. You can see for higher for fatigue testing, we can also capture the response quite well. We have mounted these as surface sensors, more like a strain gauge. And what we did there was to get the carbon nanotube web and again put it between thin glass fiber pre-preg strips and then attach that to the specimen. And what you can see is again that we can measure a change in resistance. What we do find obviously is that there is a change in gauge factor as you move up that loading. Right, this is more of the same really, looking at the difference when you load your strain sensor within an elastic region and when you then go beyond that and start loading in a regime which is inducing damage, and you can see that we capture that quite well. Again, as surface sensors, we can the response is very fast, so we can capture fatigue performance also. And the last thing I want to talk about is something which we're very excited about, and that is as a sacrificial element in thermoplastic welding. And what we've done here is we basically used a similar setup to what we had before, but instead of we've got two copper electrodes, we've got our carbon nanotube web in between, and then we've inserted this between a butt joint, and then through a combination of heat and pressure, we wanted to see how well we could fuse or weld these two thermoplastic components together. Now, as I mentioned earlier, there are certain advantages. They have negligible weight and thickness. We can control the properties of that conductivity, and of course, they're also very, very flexible. And if I look at the results here, we've looked at different energy requirements and different pressures, and you can see that you can pretty much recover the strength of a pristine sample with a combination of pressure and energy. So if specific power of 55 kilowatts per meter squared, so you've got an energy here of about 8,250 joules per square meter. That the heating there took place over about 90 seconds. Now, what's nice about this is that unlike, say, we know that there are places where thermoplastic welding is being achieved by the insertion of a metallic heating element, which then remains in the structure. Now, when you look at what happens to our web, you can't even see what happens to the web actually once the two surfaces are fused. So it almost disappears, which is actually quite a nice thing to have. So as I mentioned, it's highly flexible. We don't have any corrosion issues to worry about, and it's highly customizable in terms of heating distribution. So that is very much a work in progress. We do have quite a bit of interest there, and that's basically it. I think I've been able to hold to time, Paul, and thank you for listening. I should mention, by the way, that is NanoMan, which actually won there was a competition held by the University of Cambridge on SEM images, and one of my ex-PhD students was looking at some CNTs under a microscope, and he saw this little chap. So that they are just single carbon nanotubes. Well, the arm is, there's a few carbon nanotubes there, but anyway, I thought that's an interesting image. Thanks for listening.
You're welcome, Brian, and I'll give you a round of applause, as everyone else will. Fantastically interesting, very diverse. It's really inspiring to see such diverse applications from the material you're developing. I guess from my perspective, it's fascinating to see the scale up, actually, and the large scale applications of these nanowebs. I mean, aircraft structures, also in the welding. At the end, which was new to me. I was aware of some of your other work, but thermoplastic welding is one of the reasons I invited you today, because I saw the potential there, and you're already ahead of the game. So I guess I was going to say, you didn't say too much about the materials that you're embedding them with. So is there any limitations on the type of reinforcement of the host material, like carbon fiber, glass fiber, or resin material, such as thermoplastic or thermoset? And just before you have a little time to think about that, we've got a few questions in the QA which I've published. I'll come to that when we have time. And I'm sorry, it was remiss of me right at the beginning, in my solitude and excitement, I forgot to introduce myself. So very briefly, I'm Paul Weaver, the Bernal Chair in Composite Materials and Structures at Bernal Institute. And once again, you're very welcome to be here this afternoon. So Brian, how about my first question? Right.
So and that's a good question. And we used to always be very critical when people looked at any nano enhanced or any heating element. You put it between two non-conducting materials, right? And we've done that with glass fiber. We have also done it with carbon. Now, of course, then you still get an advantage, but then you must acknowledge that carbon is also conducting, right? So so we've looked at that. The reason why we wanted to embed these in non-conductive material was to allow us to interrogate and investigate the controllable parameters. Now, but having said that, if you look at the anti-icing system on the 787, which is metallic, again, they've encased that in non-conductive glass fiber. In terms of thermoset or thermoplastic, it really doesn't make any difference.
Oh, that's interesting. And I guess then it could possibly be integrated into a hybrid fiber system for a tape placement, or even for resin fusion or something like that, if you wanted to target certain areas for its multifunctionality, for example.
Yeah, so we have actually produced some of our samples with resin infusion or resin film infusion. Okay. there's great potential, Paul, and I'm reminded of your facilities, and we are going to talk about this. I'm
well,
sure.
we are. There's an obvious. I mean, I won't dominate this anymore, but we need to follow up this. We're ready for it. So I'm going to go to the questions. The audience can see the published ones in the Q&A, as you can, Brian. I'll read them out. So first of all, we've got Garode. In terms of manufacturing, are CNT webs easy to handle, or do they constantly need to be wound onto a mandrel? And then he gives an example. If you made a 1 meter square of a web, which lay flat originally, I mean, there's not much of it there, not much mass there, is there? So would it curl up due to potential residual stresses that are present?
Yeah, so a couple of things. We have our own facility here where it's, your wafer on which you grow your carbon nanotubes, that's going to be restricted by the size of the quartz tube that you put them in. And we are not the only, there are a few other places now making them. And my colleague Professor Stephen Hawkins, not Hawking, but Professor Stephen Hawkins, whom I met at CSIRO, which is the Commonwealth Scientific and Industrial Research Organisation in Australia, which is like the Fraunhofer of Australia. They were literally across the road from my previous university, Monash, and that's how we got all this going. He's the one who developed the webs, and I was, when I went to his lab, and his interest at the time was spinning them into yarns, and I said, please don't spin them. I want to have a look at what we can do with those webs. And of course, he's now, there is a facility in Texas which can make these at a larger scale.
Okay. Yeah, very good, very good. We've got a whole bunch, Brian, so I'm going to ask you to take that into account. Probably got 6 more questions or something coming in, so concise if we can, please. From Agaliki Chantelli, does the CNT web consist of a zigzag type of CNT structure?
Depends what you mean by zigzag. I mean, when I talk about them being perfectly straight, they're going to wobble a bit, right, as you would expect. But they don't zigzag. So the conductivity difference, the ratio of conductivity in the longitudinal and transverse direction is about 1 to 25 up to 1 to 50, right? Now, you will always get some carbon nanotubes crossing over, but they are highly directional.
Very good, excellent. Move on to Mohammed. He's got 2 questions. We'll answer one for the moment at this time. We'll come back to his second. It's basically relating to how you tune the volume fraction of CNTs for a particular sensitivity for SHM, i.e. damage detection.
The volume fraction of the CNT? Well, yeah. The short answer is we don't, right? We have a system in place which gives us a CNT of that type of uniformity, 80% optical transmissibility. Now, but it is a good question, because we can change the volume fraction, as we have done, by pushing them over, right? And then you can bring them closer together. You can increase your volume fraction somewhat. Very good,
very good. Connor McCarthy's asking more about the application by industry. So particularly, what's the view of the aerospace industry for adopting such a promising novel approach in the foreseeable future?
Yeah, it's something you'll be very familiar with. The first question they will ask is scale up, right? Yeah. But we do have some ideas as to how we may get around or identify a means of addressing in industrial type of production. But yeah, I mean, look, this is low TRL work, and we are talking to the way we're going. If it's going to go anywhere, we're not probably going. We're not going to probably see it straight away all over the surface of an aircraft. But you can't see why you couldn't have that as a replacement to the current 787 system or in a cell, right? Because there
I
is.
think it's tuning it for a specific application or location. I think that's I think a lot of promise. I agree with that, Brian. Then we move on to WS. I won't second guess who it is, but I think I know who it is from Limerick. Regarding fatigue testing for detecting damage, what R values were studied?
Yeah, 0.5. It was the one I showed you. I'm just looking at the slide now. It was 0.5.
I'm not quite sure the significance behind for the background for that question, but
well,
is there anything else
into some damage, I guess, right? It gets you into some damage, perhaps.
Okay, I get it. Yeah, okay, that makes sense. Thank you. And then we move on to Trevor, who says great talk, which we all agree to, and then saying using CNT SHM to monitor bond integrity, which is what you showed, opens up a possibility of getting primary aircraft bondage structures approved by FAA or EASA without using chicken rivets. What is the TRL of this technology at the moment?
Low.
I think you've answered that.
Yeah,
but so
because of course, you know, the issue there is, you know, you are introducing an additional system, right, to a structure, which is an additional failure point itself. Now, as you know, Paul, there's very little SHM on aircraft even today, and I think it is that balance. But what's related to that, the bigger question is not just joints, it's repairs. You know, the challenge is still out there. How do you guarantee the integrity of a repair or certify it? And that's why, you know, we have certain restrictions on what we can bond repair as opposed to repair by fastening.
Yeah, I think I agree with all your sentiments. In the end, I guess it's just convincing that it's a fail-safe process, the authorities. So, I mean, I guess you have to go through the aircraft companies for that, I suspect. But it's still promise. There's a lot of promise there, I think. So moving on to a Mr. or Mrs. or Miss Anonymous, could this CNT be used with any other welding technique, just with the CNT on its own, without the use of the electrodes, for example, to sonic welding, which is something that interests us here, particularly at Limerick? Right.
We've used it with lasers, and it's remarkable how well those carbon nanotubes absorb laser energy.
That's interesting.
So we've done that. Haven't looked at any other type, but certainly one of my colleagues, Giuseppe Catalanotti, and our PhD student has been, and a colleague Chi Chen, who's a laser guy here. We've been looking at that, and we've got some very promising results.
Excellent, very good. So we've got two more in the Q&A at the moment. We will be finishing in 4 minutes, Brian, and everyone else. And then just to let people know, then we'll be going to the announce of the competitions at 4:15. And a link will appear in the chat here. So moving on to Mohammed's second question: how much is the CNT forest, the aligned web, as you call it, deposition rate at the moment? In other words, meters squared per minute. I guess we're looking it out for scale up, really.
In terms of growing them, in terms of growing the forest, it's actually very quick. When I say quick, there is an optimum height, at least from what we're doing. It's about 250, 300 microns. But you're not waiting for hours for that. You're waiting. I can't remember. Probably about 10 minutes, right?
Oh, wow.
And then in terms of drawing that out, I mean, a wafer that size, you can get 30 meters easily, right? The draw speed is a function of the integrity of that forest. If If it's a bit ropey, you probably try to pull it too fast and the whole thing disintegrates. But you know what I showed you there is pretty much the speed at which we draw things at.
That's impressive. I mean, from what I've seen elsewhere, it looks significant. I mean, you can make other materials with it, or contribute to other materials, hybrids, as we mentioned. Yeah, it looks excellent from that perspective. We do have time for any more questions. The last one for the moment is from Walt. I think that's following up on the previous fatigue question, and is asking, just in case in fatigue, would an R of -1 be as sensitive?
Where you put the well, I can't see why not. I mean, we haven't tried it. Simply, I guess because of the nature of the specimen that we were using, if we went to -1, it would buckle. But I can't see why that would be an issue.
Well, fantastic. I think that's concludes all the questions we have for the moment, and the timing's perfect to finish for 4 o'clock. I just want to say we've had way over 100 people here this afternoon.
Fantastic.
Yeah, I think, yeah, I'm really happy with that. And brilliant presentation, sparked a lot of ideas, superbly presented with the detail. And I hope there's some collaborations with us at Limerick and hopefully elsewhere for you, Brian, in time to come.
Yeah, sure.
And my perspective, I'm sure we're going to be in touch with each other on other work that we're doing at the moment in the next few days. But for now, thank you very much. And I'm going to...
Thanks, everyone. Thank you all for listening. Much appreciated. Good evening.
And for everyone else, refer you to transfer to the schedule from the flyer for the results of the competitions and the closure of the international research aspects of the Bernal Research Day for 4:15. Thank you and bye-bye.